And moreover, we can consider a more general concept than this perfect matching. So given graph G and a function f which assigns some non-negative integer to each vertex, we say on f vector of G is a spanning subgraph H. So again, spanning subgraph is a subgraph which covers all the vertices, such that the degree of H is same as f value of the vertices for all V. Then we say this is an f vector, and we say a k vector of G is an f vector with f being the constant function, which is, for all vertices, it has value k. So this is simply k regular subgraph which is spanning. So k regular spanning subgraph is k vector. The perfect matching is actually a one vector. It's spanning because it covers all the vertices, and then its degree exactly 1. So it is a one vector, and one vector is also a perfect matching. So by using flow theorem, with this definition, let's make this smaller so that we can have I can have more space. Wait, what? So with flow, we can actually prove the necessary and sufficient condition for a bipartite graph to have an f vector. So let G be a bipartite graph with bipartition AB, and let f be a non-negative function with value integer, because all the degrees must be integer, so it wouldn't make sense to consider a non-integer value function f on the vertex set. Then G has an f vector if and only if two conditions holds. First, obvious condition is that the sum of f on A side and sum of f on B side must be same. This is quite natural. Okay, let me write it down and then explain. And for all set x in A and y in B, we have summation of all vertices in X, summation of which f value is at most the number of edges between X and Y, plus sum of all the vertices outside of Y in V, and sum of which f value. So necessity is actually easy. So if you have a graph G, and then if it has a f factor h, then degree sum of h, so summation of fv is same as summation of degree in h sum, because h has degree exactly f. Degree sum of h on the vertices on A counts the number of edges. So this is number of edges in H, and this also counts it. Every edge is counted once on the degree sum. So one must satisfy. So now we are proving this necessity condition. And for 2, why is it true? Again, if we have H, then we have this X and Y, and then this H is sends some edges. So what does this? This term counts the number of edges from X to everything. So number of edges from X to B. Because this is degree of vertices in H. This F is degree in H. And this term counts all the edges between these two sets, X and Y. And then this sum counts all the number of edges from this B minus Y to everything. In particular, these blue edges are all counted. And it may even count additional edges from the complement of X, A minus X to B minus Y. So this must be bigger than or equal to the left-hand side. So this shows the necessity. So I will not write it down as it's already in the lecture note. Or you can write it for yourself from, here. And let's prove the other direction. Suppose this holds. Then what do we do? Again, from A to B, S and T, you orient all the edges in this direction, and you orient all the edges in this direction. But giving capacity is a bit different from the before. All the original edge gets capacity 1. And let's say this is B, this is B, this is U. Then we give capacity f of B to this edge and f of U to this edge. So this edge get f of B, and this edge get f of U capacity. So for all other edges, we give capacities as well. So let me get more space. So now what do we do? Okay, I will not write down how we constructed this network, but it is clear that how we constructed this. Then G has an F vector if and only if the new network has an integral flow from S to T of value maximum possible. So if we have an f factor, you just, f factor h, then you just give the flow 1 on all the edges in the h, and then you give the maximum flow value on here, then you get the, corresponding flow. Conversely, if you have a flow with value exactly this, then these are all full. They have the possible maximum value. And if this is integral, then edges here must be all using 0 or 1. You just take the edges of the value 1, then you get the f factor h. So this is clear. Then, by the max flow Minka theorem, instead of considering max flow, we can consider what's the capacity of minimum cut. If, say, Ft is a sourcing cut, then the capacity of this cut will be at least this number, because so this is what we want to prove. If we prove that, then minimum cut is at least size of this. So that means there must be a flow with value at least this. That will conclude that there exists an f factor. So we are done. So we want to instead prove this. How do we prove this? This is actually true because let x be this s intersection with a and y with the b minus s. So again, we have this bipartite graph as before, and we have this s, and we have this t. S and t. And so those three types of edges are participating on the capacity of the cut. Then capacity is summation of all f values. So this has capacity f of b for this b, and for this u, this is f of u. So f of, say, x is in a minus x. So this is x. S intersection a is x, and y, b minus y is y. This is y. Then the size of cut is this plus the number of edges between x and y plus the f of y value for y in p minus y. So this is p minus y. So those are the sum of these three types capacity. And how large is this? This is for all, summation of f value on x in a minus x, and summation of all x value where x is in x. Because this term is familiar with this term. And from this second condition, what we know, this is bigger than this left-hand side. So we know that this is bigger than this left-hand side, and this is same as summation of fx for all x in the vertex at x. So every cut has capacity at least this value. So by max flow Minkowitz theorem, there exists a maximum integral flow with value at least this, but it cannot be more than that because I mean that's the maximum possible value. So there exists a max flow with exactly this value, which gives us an desired F vector. So this shows the theorem. So like this, the flow theory can be applied to many problems in discrete mathematics or in graphs. I mean, using this flow integrality theorem together, if you have an integer flow, then it could have many combinatorial meaning. And it's natural to ask that, so if we have this sufficient and necessary condition for a bipartite graph to have a F vector, then what about the general graph? If you have a non-bipartite graph, and then if we want to find some F vector, then what can we do? So in second chapter, we will learn about more about the vectors and matching. So in undergraduate graph theory course, we learned about several theorems about matchings and vector. And for general graph, we have this Birch-Tutt formula. I mean, Tutt's one vector theorem, which says that which graph has one vector, and Birch-Tutt formula says that what's the largest size of maximum matching in graph. For that, we consider this concept of odd component. If you have a graph, disconnected graph, then some of the components have size 3 and size order 3 and order 1, order 4, order 2. Then these two are the odd component. So this is H, then O of H is 2 because it has two components with the odd order. And we define deficiency of a vertex set as this quantity. You have S, and then in the graph G, once you delete S, you have several components. And then among them you count the number of odd components. And then you subtract by S. The motivation of counting this, considering this, is that if you have one vertex, say S, and then if you have, say, several odd components after deleting this, then if you have a perfect matching, if you want to have a matching, then you have to match this with some other. But after using this, these components has odd size. So there is no way that we can find the matching covering all of them. So at least one will be left. How many these are left is exactly the size of odd component minus size of S. So at least this much vertices will be left once we take the matching. So this value, if this value is positive, then we cannot have a perfect matching. Moreover, if this value is say K, then we cannot have a matching with size, more than this. So all the matching number has size M upper bounded by this quantity. So it's actually that the Birch-Tutt formula says that this is actually, equality for the best S. And we define the Tutt set is a set with positive deficiency. So when this is positive, Tutt's condition says that there is no Tutt set. So deficiency is always, non-positive. And then we define the deficiency of a graph being the maximum deficiency of a set. And touch one factor theorem says that the graph has a one factor if and only if it has no touch set. That is, no matter what S we take, the number of odd components in G minus S is smaller than or equal to the size of S. That's what this deficiency of G equal 0 said. And Bert's top formula says that if G is an n vertex graph, then the maximum matching size is exactly half times n minus the deficiency of G. So with these theorems on mind, now what we want to do is we want to prove a sufficient and necessary condition for a graph to have an F vector. For that, there is this useful concept of F blow up. So let's consider some function f on the vertices to non-negative number. And of course, there are some conditions that need to be satisfied. Otherwise, it's impossible to find the f vector. First is that the f of w must be at most the degree of w. So that's clear. And then let excess of w be the degree of w minus f value. So let's consider we have this graph G. And then these blue numbers are the f value. 3, 1, 2, 1, 3, 2. So all the numbers are smaller than or equal to the degree. So this has degree 4, and 3 is smaller than equal to, so this is okay. And then we write the excess. So excess degree of this is 0, and this is 1. This is 1. This is 2. This is 2. This is 2. And what do? Is we want to consider some other graph here, so that in this say G prime, if we find the perfect matching in G prime, that gives us an F vector in G. And if we find the F vector in G, then that gives us the perfect matching in G prime. Because by this Bert's-Top formula, we already know how to deal with perfect matching. So we want to change this F vector problem of G into a perfect matching problem in other graph. Then there we apply Bert's-Top formula to find the sufficient and necessary condition for us to have a F vector. So how do we do this? For each vertex B of G, we replace it with a copy of K degree, excess complete bipartite graph having parts AV and BV of size DOV and EOV respectively. So what it means is that so we put 3 vertices and 1 vertex. No, so sorry. We put the degree many vertices, 3 and 3, and this has degree 4, so 4 and 4 and 3 and 3. And then we put the excess many vertices, 2, 1, 2, 1, 2. And then we make them complete. So this is complete bipartite graph. Okay, that's what we did so far. And for each HUW in the original graph, add on H joining one vertex of AB to one vertex of AW in such a way that each vertex of AB participates in one such edge. So what it means is, which color should I use? For this one, UW, you take one and you take one and add one edge. This vertex is already used, so we will not use this vertex anymore. But there are 3 edges here, so we have 3 vertices. So you take the second one and you connect to one of these. You take this and you connect to one of these. Again, these 3 vertices are already used, so we will not use it anymore. So again, there are 3 edges here, so we connect this and this, and this and this. And then here there are 4, and 2 of them are going this way, and the other one is going here, and here, and here. So we obtain this G prime. And let the resulting graph be on F flow up of G. And it's not difficult to actually check. One can check that G has an F vector if and only if its F row up has one vector. So this is actually the concept we have learned in the undergraduate graph theory. Because if you have, say, a matching here, say perfect matching here, so we have a perfect matching. Then, let's say on here, perfect matching meaning that this vertex is covered. So there is one edge which covers this. So which forbids this, the other end vertex to be used in other edge. So this is gone. And then for the remaining 2 vertices, must be matched with the edges on other parts, which corresponds to these 2. So excess many are not covered, and then rest of them are covered. So D minus E, which is exactly F many edges, 2 edges here. So 1, 2 are covered here. And again, this one is gone. There are 3 covered. 1, 2, 3. So 2 of these are covered. 2 of these are gone, and 2 of them are covered. And then these 2 are missed, so we don't add. And 2 of them are here. 2 of them are, covered, and then only 1 here. And then this part is also here. So this specific graph, this is our H. In this H, this has degree 3, this has degree 1, this has 3, this has 2, this has 2, this has 2, exactly the degree is d minus xs, degree minus xs, which is f. So it's not difficult to actually check that the G has an f factor if and only if its f blow-up has one factor. So what we want to do is we want to take a graph G, and then we want to take its f blow-up, and then here we want to check the Birch-Stubb formula, or here we want to check whether it has a Toth set or not. And then we can find the condition where, this has Toth set. And then we can transfer back that condition to G. Then we can find the necessary and sufficient condition for G to have a f factor, which gives us this Toth f factor theorem. Which says that if G is a multigraph and f is a non-negative integer function on the vertices, then G has an f factor if and only if QST plus FT minus T G minus ST is MOS FS. Let's write that for some function defined on the vertices. Let's say GS be and S is a subset of a vertex set. This is summation of all values of on the vertices inside of that vertex set. Let's write this way. Then the condition is that this specific condition holds for all disjoint vertex set ST, where this QST is the number of components Q of G minus S minus T, where the sum of all f values of the vertices in Q plus number of edges in G between Q and T is odd. So which looks a bit artificial, but it's not difficult to show that this is actually a necessary condition. If we have an f factor, then this holds. This direction is not difficult. This was actually one of the homework problem in the undergraduate graph theory last year. So you can do it for yourself for this necessary condition, as a warm-up. So next time what we will do is we will prove this Toth f factor theorem using this Toth one factor theorem. So that's what we will do next time. So today we learned several applications of the flow theory. It has several applications to graph theory theorems. For example, like Mengel theorem, and then the matching theorems in bipartite graph, and f factor theorem in bipartite graph. And then we define this f factor, which is a specific spanning subgraph with specified degrees, and which is also a generalization of perfect matching. And we learned about this f blow-up, which is a concept where we have a G, then we consider f blow-up of G, where the existence of f factor in G is same as, equivalent to the existence of perfect matching in its f blow-up. And then we learned about this Toth f factor theorem. So as an exercise, you can show that this is an actually necessary condition. So if G has an f factor, then this condition holds. And then next time we will prove that this Toth f factor theorem holds, meaning that if this condition holds for all ST, then we can find an f factor. Yeah, this is the end of the today's lecture. Thank you for listening.